Thank you so much for the kind introduction. And yes, I'm going to talk about optics in this talk and how we can use optics not only to build really small cameras, but also do some computation in the optics. And because event-based cameras are really exciting in the sense that they can do some computation with this event-based readout, this could go perfectly together with some of the stuff that we've been developing over the last couple of years. So hopefully this talk can give you some inspiration, and happy to work together on combining these two modalities. So why did we look into small lenses? Well, if you look at modern smartphones, and this is from an Apple event from 2018, not really that much has changed, right? So we still build these compound optics for our cameras, which consists of a sequence of plastic or glass elements that have aspheres, spherical surface profiles, and we build these things with relatively complex optical simulators to in the end, cram them together to get rid of that camera bump, which is what Steve Jobs wanted, and we still haven't really done that yet. So what I want to talk about in this talk is to investigate flat metasurfaces. So metamaterials have been used and proposed for a long time now in order to perform various different optical functions. So I want to try to convince you that meta-optics, such as this one here, which is about a millimeter in size on each length, can be potentially a replacement for a compound optic. So on a high level, what do we want to do, right? So I showed you this compound lens element here from before, from the Apple camera, and we want to replace that with one thin layer of a nanophotonic element plus some computation at the back end. So sort of like a low power reconstruction algorithm that's kind of folded into the ISP at the back end. And why do we look at metasurfaces instead of diffractive optical elements or some other optical elements that would allow us to shape the wavefronts that are incoming? Well, metasurfaces have this unique property that they allow you to, with very fine control, modulate the incoming wavefront. So we have polarization control at very, very high spatial resolution. We can build different meta elements very close together at wavelength structuring that allows us to, in unprecedented ways, modulate the wavefronts that are incoming. And then if we design them jointly together with computation, that can be exciting because then we can design them in an end-to-end fashion. So that's really what we want to look at. And we're able to significantly outperform some of the heuristic designs that folks have coming up in the past, which is the metasurface design on the left side in broadband. This is actually still cheating a little bit here because I'm showing you here captures that have been acquired off a screen. I'm going to show you later in the wild captures that we also have acquired with these metasurface elements. So we're starting to get them to a level where we can look at broadband scenes, which has been tricky in the past because they're so chromatic as optical elements. So how do we do that? Right. So we basically build a differentiable architecture that consists of two elements: a differentiable forward model, which is our metasurface forward model. I'm going to go into more detail on that. That's really sort of the key invention here that we made in order to build apertures that are relatively large. So beyond 5 to 10 microns, but larger. So a millimeter or even now a centimeter is what we're building. And we combine that then with a differentiable deconvolution algorithm that backpropagates gradients via a physical forward model through the PSF all the way back to the design space. All right, so how does this metasurface forward simulator work? So it basically operates by modeling spatially varying point spread functions as a representative for the optical functions that the optical system is implementing here. And we want to implement that with a differentiable proxy function because full wave simulation is not only prohibitively expensive to compute, but also is not differentiable at all. So the idea is that we work on a sequence of processes here. So what we actually design over in the end is this polynomial basis here. So these are just a bunch of polynomial coefficients at radii from the optical axis that we optimize over. And so this is the phase function that our optic in the end imparts here. And so we design this for a single wavelength, and then we come up with a phase to structure proxy. So how do I get that phase imparted by the lens to a particular metasurface structure? I'm going to tell you in a little bit what that particular structure is. Then next step, I can come up with a model, again a proxy that maps the structure to the phase imparted at multiple different wavelengths. I can then formulate a diffractive electric field and propagate that all the way to my sensor, get the intensity, and then get the PSFs that I in the end use to blur my input image, which is then reconstructed in the end with the proper noise model in order to recover an image at the very end. And so this entire pipeline is fully differentiable. I'm going to show you how exactly we do that. So the crux of this thing is exactly this operator here. How do I get from phase? All the rest here is, by the way, Fourier optics. So you read your favorite Fourier optics book. You can implement that nicely in a differentiable fashion. But how do I get the phase to a structure of a particular metasurface that I want to design? So I haven't really told you, okay, what our particular metasurface is. We start with a very simple design. So we use silicon nitride on fused silica as a substrate. So these are 700 nanometer height pillars here that we vary in diameter between 100 and 300 nanometers. So that's essentially all the design space that we're restricting ourselves to. And here you see an SEM image of that particular optic. And so if we do that, then we can locally formulate the metasurface as sort of like a duty cycle with a duty cycle concept. We can just basically say that we have locally a duty cycle, which is the ratio of the pillar width to the local pitch. Okay, so this is something now we can actually simulate. So we can simulate a mapping from phase to duty cycle and vice versa with a traditional method. If we look at a small area, right, so then we can use rigorously coupled wave analysis, CWA, to solve Maxwell's equations and compute exactly that phase that is imparted here at that local location.
Phase of what relative to what?
Phase of the light that is incoming at a given wavelength, right? And then depending on the particular wavelengths, right? So the multi-wavelength is in the next step. So we can do that, and then we get here a mapping. So this is exactly in yellow, these particular dots, that we can then approximate again with another polynomial, right? So just a simple polynomial approximation, and that then becomes a nice differentiable mapping that we can implement in PyTorch or TensorFlow with just a few lines of code. Right? So you can obviously also approximate this if you have more complicated functions with a neural network, but because of some tricks that we made in the design, we got this nice, almost injective mapping that we see here on the right side. We can fit to it and can use that in our design. So this then becomes part of this entire pipeline here, and we can differentiate end-to-end through it, and that turns out to be about 3,000 times more faster than full wave simulation, and also memory consumption is about 3 orders of magnitude lower if you wanted to optimize for very large elements. So that's sort of the key thing to come up with this proxy, which is not perfectly accurate, but good enough for us to design these optics in an end-to-end fashion. So then we combine this with a reconstruction algorithm. Right? So for the reconstruction algorithm, lots of different algorithms have been proposed in the past. And as you know, we can use traditional inverse filtering methods or optimization-based methods that actually formulate an objective, and we try to solve that or approximately solve that by unrolling. But the key thing here is that all of these algorithms are great because they're model-based. Right? So we use the PSF in these algorithms, and that means actually that we can backpropagate gradients through the PSFs all the way to our design space, which was that polynomial at the very beginning. So that's exciting, but at the same time, they're not doing too well because we don't have any learned features. We can't use priors that efficiently. We can't use large corpuses of data very effectively. At the same time, neural networks are great at reconstructing things, but they don't have this model-based approach. So a simple trick that we did for this particular project is basically combining both. So insert into a neural network, UNet-based network, an inverse filter that then operates in feature space, and that sort of gives us both. And that turned out to work really, really well in practice. We combine these two blocks here, and then we're able to backpropagate end-to-end through that entire design and optimize for a reconstruction algorithm with features that are learned, as well as for the metasurface layer. And then we fabricate this metasurface in the end, and we take a bunch of images with it. So here's the design process of this end-to-end optimization approach. So you see the time lapse of a heuristic compared to a heuristic design, and you see that if you look at these spatially varying PSFs, they get really tiny spot sizes at what you don't see right here because the screen is not that great. You get a relatively large floor here of these PSFs. So what you basically turn your deconvolution problem in where instead of optimizing for a relatively large PSF, you get for a peaky PSF plus a large tail. So it's essentially becoming a dehazing problem, which is what these methods can handle relatively effectively. So here's some results, similar as mentioned before, compared to a state-of-the-art neural nano-optic that was a heuristic design. And we do that with a relatively small optic here that's much, much tinier than a compound optic. And if we compare those two side by side, here we can see that we're starting to get close to these conventional cameras. But I've been cheating a little bit here, because as you see, the background is black. So that's relatively easy, right? Because I'm kind of hiding these aberrations in the black background. And I'm taking these captures also from a screen. So what do we do about that? Well, so the next step that we did was recently, hey, look, maybe we can resolve this by optimizing over an even broader band. Instead of looking at 3 different discrete wavelengths, we did the entire band, and we built an array of these sensors. So this is an ultra-thin sensor, just 1 millimeter back focal length, and you can basically fabricate the optics on the cover glass of the sensor. So you completely throw away your conventional optics, and you only have on the cover glass these tiny little optics sitting. They don't have any baffles, so this is something in the future that could improve the design even better. But all of a sudden, you get in the wild captures that are pretty decent if you stitch those together. So here's a scene captured with a ground truth reference camera, and here's the reconstruction and the measurement on the left side with this array camera. And you can see that although we have these aberrations, by stitching them together, we can actually do really, really well. So hopefully that convinces you that there's lots of juice in these meta-optics here. All right, so next step. I promised you that I wanted to do some computation in the optics, right? So can we replace some of the optical stack here, and instead of concatenating it with a deep neural network that does object detection or classification, can we move some of that computation into the optical stack? So that's an interesting question that we looked at. And obviously, optical artificial intelligence, or ONNs, have been looked at for a long time at this point, and folks have been trying out various different approaches how to cram some computation into the optical stack. So since the 50s, there have been various flavors of how to do that. But if you look at where we are now with optical neural networks, then the most successful systems use ensembles of deep neural networks of up to 30 optical neural networks, or SLMs, to do that. So they're really impractical, and they don't do all that well, right? So the best approaches that we have today are reaching roughly about Linnet performance for classification, which is not very good, right? So that's an old network from the 90s. Meanwhile, we're still 15% off in terms of CFAR, which is also a traditional metric, right, that the computer vision community has long passed. We're 15% worse than AlexNet, which is sort of like the very first modern neural network. Okay, so we asked us, okay, now we have this array design, so can we cram some of the computation into the array? So we start with the nanophotonic camera design from before, the single metasurface, and then we say, okay, well, we can compute some kernel, some convolution with a given kernel with it. But now we can also build this array here, right, and cram a lot of kernels here over our sensor. So we can build an array, and I want to convince you that a 5x5 array can actually result in 175 spatially varying optical kernels. So that increase can be quite significant if you do 2 specific tricks that are tailored to the neural network design. So the first one is in the optical domain, we can actually do really large convolutions, right? With almost arbitrary kernels, because we have these meta lenses now, we can tailor them really, really well. However, in deep learning, we want to use relatively small kernels, but a lot of them, and ideally nonlinearities in between, right? So let's consider this 7x7 convolution with a stencil shown here. Then we can actually formulate this thing here also as a sequence of 3 3x3 convolutions. K1, K2, K3. So that becomes essentially a convolution of these compounded convolution kernels. So now the number of parameters that we see if we do this simple factorization is actually much lower, right? So if you look at the 3x3 kernels, convolve 3 times with them, right, then we end up with 27 parameters. Meanwhile, the full 7x7 kernel obviously has 49 parameters, right? So we end up in practice, if you run a simple regression, which I'm showing you here, with a lower dimensional space that, if we implement this in PyTorch or TensorFlow, works really efficiently because we can use these small kernels and operate in this low dimensional space. So this works much better, and we can get much better results if we factorize our kernel into a sequence of a lot of small kernels. Right? So just one trick. Now, we can actually make use of the spatially varying nature of these aberrations as well, and cram a low-dimensional parameterization with a per pixel differing spatially varying kernel into our PSFs as well. So we can make these kernels vary spatially, and we can design how they vary spatially all over the sensor. So with these two tricks, we're able to, out of this 5x5 metasurface array, to get 25 channels, which then after ReLU, which is exactly the first non-linearity that we want to apply right after, some average pooling, some separable convolutions, we get some really high quality results, which I'm showing you afterwards. Okay, so now the overall max, so multiply, accumulate operations are about 0.1% on the electronic side, and almost everything, so 99.9%, are done in the optical domain, because of these two factorization tricks, right? So the large kernel factorization as well as the spatially varying kernel factorization. So that brings us now with this approach to AlexNet performance. So all of a sudden on blind CFAR, we reach about 75% blind testing accuracy in practice on an experimental setup. So it's kind of like the first work that with a single sensor, not 30 ONNs achieves really good performance on AlexNet. So first step to get there, here's some visual examples on MNIST, which is too easy, and here are the examples on CFAR. So this is not perfect, but at least we're now at AlexNet performance in a thin form factor without these really large ensembles of stacks of diffractive layers. Okay, so last thing that I want to convince you of is that we can do these, that we can use these optical elements to do really cool stuff that I would call superhuman vision. One example would be that we can approximately see through obstructions, right, and allow us to use the camera and turn it into an obstruction-aware imager. So for this automotive scenarios, we're assuming that we have a camera behind a windshield, so a glass surface, and then the camera behind it. And if you want to capture a scene like this, then hopefully we detect the pedestrians in the scene if it's an ADAS system. So now occlusions from soil or raindrops or bugs on the screen make this challenging. And if I now take my favorite in-painting method, I manually even segment these areas because they're difficult to automatically segment, and I in-paint them with Llama, then I don't get really great results. Now, if we learn nanophotonic layers similar to the ones from before, we insert this into the aperture plane, then we can actually get really good reconstruction results if we combine this with a neural network reconstruction method. Okay, so how exactly does this work? Conventional camera, here we have a scene at optical infinity, and if there's objects at optical infinity, they get mapped to different spatial locations on the sensor. So now obstructions close to the camera, on the other hand, lead to blur that kind of approximately alpha blended as a really approximate crude model of the image. So we can actually make use of this blur of objects that are close by and tailor it, design it by inserting a nanophotonic modulator. And so if we now combine this with a reconstruction method, similar to the reconstruction method before, that's PSF aware, so that allows us to backpropagate gradients through the PSF all the way back to the parameterization of our optic, then we can train this in an end-to-end fashion together with the network as well as with the with the optic in a joint fashion. And we do that with simulation. And what comes out is quite interesting. So without any intermediate losses, just saying, okay, we'll try to get the best image out that's as close as possible with a per pixel L2 loss to your target simulated image, we get these results here. So what I'm showing you here from right to left is from near to far. So far is on the very left side. You see a peaky PSF. And on the top, what I'm showing you is a conventional lens. On the bottom, this optimized lens that you see here. So if you now have an occluder at 20 centimeter distance, then what happened is that this lens learned to actually come up with these very large rings here. So it learns to chromatically spread all the information that's close all over the entire sensor and give us these outputs here. So it essentially, again, turns this occlusion in painting problem into a dehazing problem, which is what these networks at least can do better than making up information, hallucinating information that's not as accurate as possible. And compared to a random diffuser, this doesn't help us too much. The random diffuser does not really do well for these cases because it blurs over the entire range. So that's not really an alternative. So now we built this setup. Here are some experimental results acquired in the lab where we have here a reference scene. Now, let's say these are occluders. So these diagonal stripes here that we place on a glass surface in front of the camera. Now we insert our modulator and try to get rid of it with conventional inpainting. So the inpainting doesn't do well. So structurally and semantically it is not able to recover the scene adequately. And we can do substantially better by this reconstruction. I'm going to show you this example here before. So here we get actually the fine structure back. There's still some artifacts, but you can see that, at least in principle, this is working, and we can get the fine structure on the mushroom and on the owl's eye back here in this example. All right, with that, I'm at my 20-minute mark. So in summary, we looked at neural nanophotonic cameras that can allow us to build ultra-tiny cameras, cram some computation into the optical stack, so allow us to do neural network computation, partly in the optics or mostly in the optics, and aim to what I call superhuman vision capabilities in the camera. I'd like to thank you all.